I'm excited for this video to talk a little bit about lactate and some adaptations. Now, before we get too far into things, just want to talk a little bit about lactate and how it comes about through our metabolism. Lactate, for the most part, is going to really start with the process of glycolysis with our 6-carbon glucose molecule. Now, once we have glucose, the process of glycolysis is going to keraoticize or chop that bad boy in half into 2 3-carbon molecules called pyruvate. What's going to happen next really depends on whether or not there's oxygen present or not. If there's oxygen, then it's going to go through its normal mitochondria stuff and make a ton of ATP. Now, if there's no oxygen present, then a different process happens called lactic acid fermentation that makes lactic acid, which is different than lactate that we'll get into later, but it makes lactic acid. So what's the big deal? Well, the big deal is this. This process over here, okay, needs NADH to make a whole bunch of ATP. This process over here needs NAD+. Once the NADH is used, it becomes NAD+ to go back to here. So these two help each other out. However, when there's no oxygen present, all of the electrons and hydrogen are stuck here, which means there's no NAD+ for glycolysis to make ATP. So this process right here of pyruvate converting to lactic acid and lactic acid fermentation, the main purpose of that is to take this NADH that's stuck and convert it back to the NAD+, so glycolysis can still keep rolling and make an ATP when there's no oxygen present. So this lactic acid that's made through fermentation doesn't stay as lactic acid very long. So really what happens is as soon as it's made through fermentation, it's dissociated, which is a fancy term for it loses a hydrogen, the lactic acid part of it does, to become lactate. And that's how it's going to move around in the blood and the interstitial fluid and for the most part transport dang near everywhere. There are some other things that happen to the lactate that get added on and buffered and salt and all this stuff that we'll get to later in the video. But big, huge point. These two things are oftentimes used interchangeably, but that's really incorrect. They're different items. Lactic acid and lactate are different. Lactic acid is what is immediately formed, and lactate is what is converted to after it loses that hydrogen. Lactate buildup, that doesn't sound very good. Oh, well, what do you think? Yeah, it's going to be okay. So let's stick with me here. So as we start out in the muscle tissue, okay, muscle tissue is going to use glucose through glycolysis and other things and break it down into pyruvate. And if there's not a whole heck of a lot of oxygen present around for whatever reason, could be a lot of reasons that we'll get to later, we're going to make our lactic acid that will convert to lactate. And then the lactate will go through the interstitial fluid and into the cardiovascular system, and from there make its way to the liver. From the liver, the lactate can then actually be produced back to pyruvate, and from pyruvate, making glucose. And then back into the interstitial or blood, fluid or blood, and make its way back to muscle tissue. So now the muscle tissue can use the glucose that was just combined from the liver. The muscle tissue can use that same glucose to keep producing ATP for energy transfer. Two other things that are kind of cool to talk about in this capacity is fast twitch muscle fibers are actually going to release some lactate, but then when they're going to do that, other fast twitch or even slow twitch muscles are going to take up that lactate and they're going to convert it to pyruvate, and then the pyruvate's going to go to the mitochondria to break down, as long as there's oxygen present, break down and make a ton of ATP. So that's another example where the lactate that's made is also getting used, which is called lactate shuttling. The second one that's pretty cool is at high intensity levels of 80% or greater, Inactive muscles are going to release lactate into the bloodstream, and then through the Cori cycle are going to help keep our glucose and glycogen levels high for the active muscles and the active tissues that are working. Big picture here is that just because our muscle tissues are producing lactate, we also have a process to use lactate. So there should never be a situation where lactate becomes too high or too low at an exponential rate just because we're exercising. Even though lactate that is made will also be used, there are some circumstances where an imbalance can strike. For example, if the Cori cycle has an issue with the rate of oxygen delivery, that could be bad. If for whatever reason that's slow, Another reason would be if for whatever reason the oxygen consumption is way higher than the oxygen that's being provided. So what does that mean? Well, oxygen perfusion could be a potential issue. Blood flow could be slower, right? Capillaries not activating, or they're dilating or constricting when they shouldn't be, and things get clogged, and we're not able, like the inactive muscle tissues aren't able to provide lactate to go through the Cori cycle. Enzyme function is slowing down because of repeated use, faster than what the citric acid cycle and the electron transport chain, the part of the mitochondria, can keep up with. But really what it comes down to is this guy: intensity and duration. The higher the intensity and longer duration, the more energy is required, right? It takes more energy to do more intense things. The more energy that's required, the more oxygen is required. The more oxygen that is required, the more potential issues for oxygen delivery, for oxygen consumption that there would be. Keeping on this train of intensity and lactate concentration, at low intensities in exercise, really whatever's made in terms of lactate is going to also be used in the Cori cycle. So we're not going to see an overall increase at lower to moderate intensity levels of exercise. However, at higher intensities, well, with higher intensities requires higher energy demand, and higher energy demand is also going to make higher oxygen consumption, which we just went through. Also means that we could increase the possibility of making lactate through the conversion of lactic acid and after lactic acid fermentation. The lactate threshold quickly is the highest amount of oxygen consumed that's going to raise the blood concentration levels of lactate no more than 1.0 millimoles in concentration of lactate. Okay, we've been cruising around at low intensity, right? Not really much of anything. And then let's say that this represents 1.0 millimole, right, of an increase. And then, wow, it's going to kind of climb a little bit. Okay, so that 1.0 would represent our lactate threshold. This is an over-exaggeration just to overemphasize that concept of steady eddy and that it increases. So then we have our onset of blood lactate accumulation. Very much like our lactate threshold, the major difference here is that it's at a 4.0 millimole increase of blood lactate. Same thing before our pre-exercise levels. If we get this increase in 4 millimoles in concentration of blood lactate, that's when we're going to have our onset of blood lactate accumulation. At the end of fermentation, lactic acid is made, and this lactic acid, as we said before, is going to quickly dissociate into lactate. So to help facilitate that process is a buffer sodium bicarbonate. And the sodium bicarbonate is going to react with the lactic acid to form sodium lactate. And also bicarbonate. Breaking this down just a bit further, the bicarbonate is going to break down into water and carbon dioxide. Now, carbon dioxide can become toxic if we have too much of it, and most of our systems around our body and our blood, especially around our aorta and around a carotid artery, have special chemoreceptors in there that are going to trigger, hey, we have too much carbon dioxide around here, we need to get rid of it, and so our body is going to pump blood and exhale and breathe at a more proficient rate to get rid of the carbon dioxide and act as a physiological buffer as well. So we got our chemical buffer working, we have a physiological buffer that's triggered by the production of this carbon dioxide. All of this is fine and dandy to help prevent a change in pH to make things that are more acidic. But our buffer, okay, our buffers are key to this whole process. So the more lactate that is produced, the more our buffers are being used. The more the buffers are being used, the more acidic our blood becomes. Not good. If we have our oxygen consumption here, where 0 liters, we'll say 5 liters over here. And so some form of intensity. And over here, we'll have lactate levels. And then also minute ventilation, where it would get progressively higher in units. Big picture stuff. As intensity increases, our lactate levels are going to increase very, very slightly, up to a point, and they'll get progressively bigger and larger and larger and larger. Our minute ventilation is going to stay at a pretty easy breezy pace to be able to deal with everything until we reach our ventilatory threshold, which basically means our rate of ventilation, how fast we breathe, is going to increase at a rate faster than intensity increases or oxygen consumption increases. That same point's right around lactate threshold. So if we said this was our lactate threshold, for argument's sake, we'll say, that 4 millimole location is going to be our onset of blood lactate accumulation. Also, right around that same point, we're going to see another spike in our ventilation rate, our minute ventilation. And that's our respiratory compensation. That's another increase in our minute ventilation in response to our increase of lactate accumulation to try and buffer off as much acid as we can. We're going to try and breathe off as much carbon dioxide that's been buffered from our last slide. Training adaptations as related to onset of blood lactate accumulation is pretty cool, primarily because it's independent of our VO2 max or oxygen consumption. So our blood lactate accumulation, it's a great indicator of performance. And specifically, some of those adaptations that would help us predict performance would be muscle fiber type, being into a more slow twitch or type 1 in an endurance capacity, our number of mitochondria and their size, our blood vessel density, which is a fancy term for saying we're going to have more capillaries in the same area and around our muscle tissue so we can deliver oxygen better, right? That's good. And then the enzyme activity, that all those enzymes that are going to help perform the chemical reactions around there, they're going to be able to have more of them and be more sensitive and have a better affinity for all their substrates that they're working with to allow that energy transfer to ATP to happen much more efficiently. All is going to increase our onset of blood lactate accumulation farther down to a higher intensity, right? Which is just going to help delay all of the negative bad accumulation stuff and help us perform longer and better. Speaking of performing longer and better, there's those that say that it's a totally mental item. Chimera and Nazar did a study in 2010 that actually showed, this is pretty cool, that onset of blood lactate through endurance training also increases the cognitive abilities, or really our neural ability to depress anything that's going to go on with our thoughts about fatigue, and helps us control our muscles and our movements of our muscles much better through training. So it's another adaptation that helps our mind deal with our sports performance. And for this video, it's been a blast talking about all these wonderful things with you, but that is all she wrote. And thank you again for giving me an extra day, Dr. H. Appreciate it.